All right, so here's our end of this topic set. We are now reviewing everything that we've talked about so far. So I've started with a clean slate, and I'm just going to kind of brief everything again. You may remember that we kind of started our introduction by looking at kind of how all of this energy stuff is going to relate. And so really that's what it's about. This is the unit that's all about energy. Okay? And essentially we always look at the energy that we start with is always going to be equal to the energy that we end with. Okay? This is what it means. It's the conservation of energy. So the energy that we start with is equal to the energy that we, or the energy that we start with is equal to the energy that we end with. All right. So now because we're talking about energy, we're always talking about something that's measured in joules. And so what are the ways that we can get joules? Okay? Well, we know that joules come about any time that we have, let's see, what was the units again? Kilograms, meters squared per seconds squared. Okay? That's how we got our joules. Okay? Anytime we're at a combination of those units, that's how we get it. So, big key things. We started with work. Work was a force times a distance. The key thing is same direction. And you can notice I did change that on the board because it had been driving me nuts. I just hated seeing that cosine theta there because ultimately you just need to look at the force and say, is that force in the same direction as the displacement or as the distance that I'm going? And if it's not, find the triangle that makes it so, okay? And so that's why we look at it in terms of like the force parallel lines, okay? So in other words, work is nothing more than a force times a distance. Well, a force is a mass times an acceleration times a distance, so I'm just breaking it down. Again, kind of going back to the first thing that we did when we talked about fundamental quantities versus derived quantities. Work, definitely a derived quantity. It's a mass times an acceleration times a distance. Mass is usually in kilograms, acceleration is in meters per second squared, and distance is in meters. Oh, same units, okay? Anytime we get the same units, we know we're talking joules. And if we're talking joules, we're talking energy, all right? So that was one way that we looked at it. We looked at it from the kinetic energy standpoint, okay? Kinetic energy. Kinetic energy was 1/2 mv squared, all right? So if we look at this, okay, m is in kg, v is in meters per second, but we're squaring that whole thing, which means that we are at kg m squared over s squared. Same units, okay? Definitely talking about joules. Then we talked about potential energy. And potential energy came in two forms. There was the gravitational potential energy, which was mgh, and by the way, kilograms, meters per second squared times meters, same units. And then we also had the 1/2 kx squared, where the k is in newtons per meter and meters squared, but a newton is nothing more than a kilogram meter per second squared. This meter cancels one of those times a meter in same units, okay? Lo and behold, everything comes out to be joules, and that's what we want it to be. Now, again, big concept. The energy that we start with is equal to the energy that we end with. That's the conservation of energy. So, if we look at it in that sense, energy in, or initial energy, equal to final energy, okay? Initial energy can be any of these types of things. It can be kinetic energy, it could be potential energy, okay, due to gravity. It could be potential energy due to elastic, okay, springs. And if we look at it from the other side, our final energy could be kinetic energy, it could be potential energy due to gravity, could be potential energy due to elastic. Okay? So on a broad sense, all of those things are in play. Now, most of the problems that you saw in the problem set didn't deal with that. Okay? In fact, our roller coaster analysis dealt just with this, where we looked at the kinetic energy versus the gravitational potential energy at any of the points. Now, of course, if there isn't any, if this is not true, then why isn't it true? So why wouldn't we be able to conserve energy? Well, it must mean that there's something out there that is a energy consumer. And our biggest energy consumer is a friction force, okay? So when we see that energy is not conserved, it's because there's a friction force applied. And so in other words, our total energy, okay, or our energy is equal to then the kinetic energy that we may have, plus the potential energy that we may have, plus whatever the work done by friction is. Because remember, work is just another way to talk about energy, okay? So this is my friction. That's the loss. Okay? So when we lose energy in the form of friction. Okay? Now, we also can figure out friction forces then if we know certain things. The other way that we kind of talked about this, okay, so our other big idea was that if I'm going to have my velocities change, okay, if I have an object that's in motion or at rest and all of a sudden it changes to have a different velocity, I have two different kinetic energies, okay? So anytime I see a change in kinetic energy, I had to apply a force through a distance, which means that I had to do some kind of work, okay? So work was always equal to the amount of change in my kinetic energy. We usually refer to this as my net work, but remember, net is just something that we can throw in there. So that would give me the change through that. If I wanted to look at it and the only force that's being applied is, say, a frictional force, I could look at the work done by friction as the change in my kinetic energy. If the only thing that's causing my object to move is an applied force, okay, that applied force would be here, okay? So in other words, it would be the work done by the applied force, okay? It's really about looking at work from a sense of what is the force that's causing that motion to change, okay? We'd like to see when it's 1/2 mvf squared minus 1/2 mvi squared. We like when one of these is 0 meters per second, okay? Because it makes the math easier, okay? And typically we always see something at 0 meters per second squared when we have something at rest. Oops, and did I do that in the last slide? Oh, I tried not to write over. I apologize if I'm writing over my picture here. I don't always see that. In fact, I'm going to put a post-it note there so I don't write any more that direction. All right. So my net work is always equal to that. That's one way to kind of look at things. Let's see. We like to look at work. Work is always, again, a force times a distance. Forces are always just masses times acceleration. If we take a mass times an acceleration times a distance, we've done work, okay? That's just another way to look at how we do work. Let's see. We had to maybe do some free body diagramming in order to figure out what the force was. And so again, you may have to do this where you have to do those free body diagrams. And I'm going to just quickly draw an example free body diagram, F of G, F of N, and let's see, force applied, and maybe there's a force of friction, okay? So again, free body diagrams, I should be able to look at them and say what's going on here. Now, ultimately, I look at it and I say, what is my direction? Okay, so in other words, this one has a component going this way, this one has a component going this way. When I look at this, I say, hey, I've got a force normal, I've got a component of this force that act this way. These two, sorry about that. These two forces right here have to be equal to this one if I'm not moving in this direction. Okay, it's about that equilibrium stuff. If this component is bigger than this one, so if this this part of the applied force is a bigger arrow than my frictional force, I have net force. And usually the net force would produce a net work. Okay? If the friction force is equal to that, so these two are equal, then I'm either one of two things again. I'm moving with no motion, I'm at rest, or I am moving at a constant velocity. And that's usually what we see, is we see constant velocities, so the arrows are equal. Just another ways to look at how we kind of get to those forces, because if we can get to the forces, we can get to the nets. I just want to back up a slide here. We did take this from an energy point of view, okay? And the thing is that our problems, when we look at them in terms of energy, we can solve them that way. The other thing that we can do is we're now down to the point, okay, if I look at this, I have velocity and a velocity, and then maybe I have a force times a distance. I have a distance, and force is nothing more than a mass times acceleration. In fact, I'm going to write this over here, okay? Mass times acceleration times distance is equal to my, because that's work, okay? Change in kinetic energy, 1/2 mvf squared minus 1/2 mvi squared. So in other words, that's my change in kinetic energy. The masses, as long as the mass remains the same in all situations, it's factorable and cancelable. Okay, I can cancel that out. So now I'm looking at something that just looks like this. AD equals, I have 1/2 in each, 1/2 VF squared minus VI squared, okay? Bring that over, I get 2AD equals VF squared minus VI squared. Oh, hey, I get VF squared equals VI squared plus 2AD. Bingo! We're back to kinematics, okay? So it's like we've kind of come full circle. We started by learning about kinematics, the stuff that Galileo was telling us, okay? We got those relationships where we looked at velocities and accelerations and a constant acceleration, and we got to that point. Then all of a sudden, we switched, okay? And we started to talk about forces. We learned what Isaac Newton was telling us. And Isaac Newton said, this is how it's going to be, F equals ma. He related it back to that acceleration. Then we started to look at energy. All of a sudden, energy brought us right back to kinematics, okay? It's the tie-in between everything, okay? And that's what we study, is we study energy. So the big thing that you need to know is about energy. Energy going in equals energy coming out, as long as it's conserved. If it's not conserved, that means there was something that was taking it, energy, something like friction. The only last thing we need to talk about, and that was our other thing, was power. Power was the rate at which we change energy. Okay? So in other words, power was nothing more than joules per second. Okay? It was the amount of energy that we had per unit time. Okay? And so there we go. That's all of everything that we got. We've got all of our formulas on the board. If you have any questions, review a different video. That's always a good point. Go back and check websites. That's all I got. Hopefully you kind of understood everything, and good luck on your test.